Okay, calculus. Sorry, my battery that was beeping and dying uh, died, and so my last video got cut off. So I'm going to. I have it all. I didn't erase it. I'm just going to talk through problem number 4 on the review sheet. So problem number 4 said that you were given 20 feet of wire, and you are going to use that 20 feet of wire to make two shapes in a way that will maximize the area, the total area of those two shapes. And so this is going to be a square and an equilateral triangle. And so I'm a more visual person, so I drew this out for myself. So as we know, obviously an equilateral triangle has three sides that are the same. I call those sides x. And then a square is not necessarily going to have the same sides as the triangle, so I have to make that a separate variable, and I called it y. So we know we have 20 feet of wire to make these shapes. We know we want to maximize our total area. We want to find the dimensions of the square and the triangle in order to maximize that area. So primary equation would be the area. That's the thing that we want to maximize. So the area of the square is y squared. So this is the square. And the area of the triangle, so it's an equilateral triangle. Of course, triangles are 1/2 base times height. So, but for an equilateral triangle, that turns out to be, I don't know if you like have this as memorized in your head or you can look it up. It's the square root of 3 over 4 times the side squared. So square root of 3 over 4 times x squared is my area for the triangle. So that's my thing that I want to maximize. My secondary equation is I now have 20 feet of wire to do this with. So 20 feet of wire is going to be my total perimeter, which is 3x for the triangle and 4y for the squared. And feasible domain is going to be somewhere between 0 and 20, right? Okay, so I take my primary equation, which is this one, for area, and I take my secondary equation, and I'm going to go to my secondary equation and solve for one of my unknowns. I solved for y. So I said y is equal to 20 minus 3x divided by 4, and I simplified that out to be 5 minus 3/4 x. So y squared is 5 minus 3/4 x squared plus my triangle area, which is the square root of 3 over 4 times x squared. And if I clean that up, this is what I end up with. So I just expanded this out and then cleaned it up. I kept it. Okay, this is where I get a little weak. I kept it in radical form, and then at some point just flipped over to numbers. I know obviously in mathematics we like to keep things in clean radical form. I'm coming at you from science where I'm more like, what's the actual number? In this case, because I have an actual physical thing, 20 feet of wire, how do I cut this? You can right away, if you want to put these in and get them as numbers, you can do that. So instead of having this long thing, 9 plus 4 times the square root of 3 over 16, now I kind of forget what this was, but you can write this as the decimal that it was. I think it was 3 point something. Okay, so although it looks like a long thing, it's really just a quadratic function. So it's a very easy derivative to take. So if I take the first derivative, I end up with 2 times 9 plus 4 times the square root of 3 over 16, so just a number quantity times x, minus 30 over 4. And if I solve this, so I ran out of board space, as you can see. So I trust that you could, especially I just put these in as numbers. If I solve this for x, I get x is equal to 3.76, and then I can use that to solve for y, and it's 2.18. Now, the question is, and this is where this is a trick problem, you know, I didn't yet show my calculus to prove max or min. Okay, so let's come to this first derivative. I'm going to use the second derivative test. That's the easy way to do it. The second derivative of this function is just this number, and it's a positive number. So 2 times whatever, 9 plus 4 times the square root of 3. You might not be able to see because I'm writing really small. The point is just a positive constant number. The second derivative is a positive number. What do we know about when the second derivative is positive at a critical point? So the critical point being this. Well, when the second derivative is positive, it's not a maximum, it's a minimum. So if we go back to my problem, maximize the total area is what it says, not minimize. So these would be my dimensions if I were trying to minimize the area. So it doesn't work there. So then what you do, we haven't really seen one of these, is you think, okay, let me think about my endpoints. What if I don't cut the wire at all? So if I take all 20 feet, because cutting the wire gives me one critical point, and that critical point turned out to be a minimum. So if I don't cut the wire at all, if I just make one shape, so it's a trick problem. If I make one shape, what would the dimensions of that shape be, or which shape should it be to get my maximum area? And so what we would say is between the square and the triangle, just think about them. If I put 20 feet into one or the other, it's the square that will give me the maximum area. And so if I take 20 feet and fold it into a square, it's going to be a 5 foot by 5 foot square. So the answer to minimize my area is just make it all a square, to maximize, I'm sorry. The answer to maximize my area is to just make it a square. Get rid of the triangle, and it's going to be a 5 foot by 5 foot square. So whatever you can do to get the most of the wire as a square gives you the maximum area. What we did here is we used all this calculus to prove that at the critical point we have a minimum. So if this problem were asking me the same thing, except, or not the same thing, but if it says I have 20 feet of wire, I want to make these two shapes, how can I do it to minimize the area? Well then, here's my answer. It's going to be a triangle with sides 3.76 feet, was I in feet or just feet, and a square with sides 2.18. So there's my minimum. Maximum, no critical point matches it, so we make everything a square. So that was a little bit of a tricky one for sure. The last two problems in the homework set do some of this, like two shape stuff. You do still need to show the calculus process because you're going to use that to make your point. And I did ask you about both maximizing and minimizing. So you'll get a little bit of practice there.